All right, good evening, everyone. So yeah, my name is Dan, and today we're going to be examining the diamond surface through theory, experiment, and applications. So I'll start by introducing the system in question, which I find quite fascinating, which is the hydrogen-terminated diamond surface. And okay, I know I said theory, experiment, applications, but I will actually go applications, theory, experiment, because I think that motivates the work a bit more. So I'll start with looking at applications to field effect transistors, chemical and pH sensing, and charge state control of quantum sensors. After that, I'll talk about the theory, which is just our Schrodinger-Poisson solver that we've been developing to describe the electrostatics of this system. And then I'll go into some experiments to validate that model and provide directions for future work. So we don't normally think of the material diamond as a conductive material. It's sort of a bona fide insulator, really, but it's actually a wide bandgap semiconductor. And as it turns out, about 30 years ago, actually, it was first observed that when you expose a diamond to a hydrogen plasma, it starts to conduct electricity somewhat anomalously. And it turns out that this is entirely confined to the surface, and it's purely hole conduction. And measurements of the hole density suggested that this is actually a quasi-metallic surface now, which means that the Fermi energy has actually dropped into the valence band at the diamond surface. Further observations throughout the years showed that, for instance, if you hydrogenate a diamond in a plasma and immediately transfer to ultra-high vacuum, it no longer conducts, and it will only conduct when you expose it to air. And so that really suggested a chemical origin for the phenomenon. And it was not until the year 2000, actually, that the accepted explanation for what was going on here was put forward, which is that the dipole moment of the CH bonds at the diamond surface causes spontaneous hopping of electrons from the diamond into the lowest unoccupied molecular orbitals of atmospheric adsorbent molecules. And so what that does is it creates this almost this nano parallel plate capacitor where you've got negative charges from the atmosphere building up on the diamond surface, but you've got corresponding holes underneath the diamond surface, and they're squeezed together very tightly. And so that electrostatic interaction stabilizes what we call a two-dimensional hole gas. And so these are just on the bottom, you can see some images of or graphs, I should say, of the wave functions associated with that hole gas. Now, in terms of applications of this, because diamond has the highest known room temperature thermal conductivity of any material and a breakdown field in excess of about 10 megavolts per centimeter, which dwarfs any other semiconductor, that it suggests possible applications of the hydrogenated surface in high power or high frequency amplifiers. So, for instance, output stages on 5G or radar systems operating above 50 gigahertz. In addition, it's been found that by modifying the surface adsorbent chemistry, you can change the hole carrier density, which makes intuitive sense. And this has been used to demonstrate very effective pH sensors based on more along the lines of my research. It's also been shown that by changing the diamond, the adsorbed surface charge, for instance, by deliberately gating with an external electrode, you can modulate the ionization state of lattice defects just beneath the diamond surface, just below this hole gas. And so if these are luminescent traps, so the most famous of these being the nitrogen vacancy defect or NV center, this will also change their emission wavelength. And so this has been shown in a previous study where the authors were able to apply gate voltages to reversibly and controllably switch a nitrogen vacancy center from its negative to its neutral charge state and vice versa. And this has applications, for instance, in multi-frequency single photon sources. So a large number of diamond color centers have now been identified which act as single photon sources, and being able to electrically and on demand change their emission wavelength would be highly desirable in, for instance, quantum communication and cryptography protocols. And then this is also useful for instance, quantum memories, where by discharging a nitrogen vacancy from its negative to its neutral charge state, you can essentially turn off its electron spin interactions with nearby nuclei. And this allows one to preserve the nuclear quantum states for longer periods. Okay, so this slide is a bit of an eyesore, so I'll get through it very quickly. But for the theory here, essentially to understand what's going on and therefore to design better diamonds to optimize these applications, we want to understand the near surface electrostatic environment in the diamond. And to do that, you need to solve the coupled system of the Schrodinger equation and the Poisson equation in a self-consistent manner. So we've written our own solver to do this, which also allows us to, for instance, look at the effects of arbitrary mid-band gap surface defect states, which turn out to be quite important for diamond, and also to examine arbitrary depth distributions so that we can look at the near surface material properties. Okay, so models are great, but they obviously need to be tested. So in order to pursue verification of this model, one thing that is easy enough to measure, especially with the nitrogen vacancy center, is the electric field. So it turns out that the electric field splitting of the nitrogen vacancy defect that I mentioned before is detectable optically using a technique called optically detected magnetic resonance, or ODMR. And so if you've got a dense layer of these nitrogen vacancy defects near the diamond surface, then this can actually allow you to basically take a photo or an image of the average electric field due to those charges built up on the diamond surface. And I say average because while we would like to be able to pinpoint along depth exactly what the field is, really all we can do is measure aggregate luminescence from the nitrogen vacancy layer here. But still, if our model predicts a particular average E field, then that's what we should measure, and indeed it is. So thankfully, this agrees with our experiments. Here's a diamond that has a nitrogen implant with 10 keV and a fixed density. So if we were to use the results of the model and say that that diamond is oxygen terminated and has no atmospheric adsorbate charges, then we predict that the average E field seen by the nitrogen vacancy should be about 350 kilovolts per centimeter. Whereas if we assume it's hydrogen terminated and has the accepted surface acceptor charge of about 1 × 10⁻13 per square centimeter, then it predicts about 420 to 430 kilovolts per centimeter. So if we go over to our actual experimental results, this is actually exactly what we get. So this is our ODMR image on the right here in panel B. And so we have an oxygen terminated region of the diamond surface, which is the darker region, and then a hydrogen terminated ribbon here, which is the brighter region. And that, that we see average electric fields in these images that are very commensurate with what the model predicts. In addition, we have a way to also essentially just use the NV photoluminescence to measure the 2D whole gas density near the surface. So throwing it back a bit to that experiment where the NV charge state was reliably switched from NV- to NV0. So as the whole gas density increases, you get more and more NV- centers recombining with holes to create NV0 centers. And so if you're measuring the photoluminescence of the NV-, the PL signal decreases, and correspondingly less holes, more NV-. So by doing this, we can actually image essentially the surface potential along the diamond surface. So if we have a simple source drain and a hydrogen terminated ribbon, and we apply some source drain voltage, we can actually see the surface potential as reported by the charge states of the NVs. And why this is interesting is that by taking the gradient of the surface potential, you have the surface electric field. And so what this means is that using the ODMR signal of the NV, you can measure the Z, the electric field into the diamond, whereas by using the charge state imaging, you could measure the XY, or the in-plane electric field. And so hopefully one of the future directions of this research is that we will be able to do full electric field vector imaging of electronic devices fabricated on the diamond surface. So to summarize, I think hydrogen terminated diamond is really cool because it features this rapid transition between insulating and quantum confined quasi-metallic states. And then combining that with the favorable bulk properties of diamond, it shows immense promise for high power and high frequency electronics, chemical and biosensors, as well as quantum sensing and information. And we've developed a model that can reliably predict electric field strength, surface potentials, and charge state populations. And some forthcoming results that we hope to submit for publication very soon will demonstrate the use of this model in an optimized sensing application. So thank you very much to Materials Australia for putting this on, and thanks everyone for listening. And the Schrodinger-Poisson solver is available for free on the Python repositories, but I can't guarantee it won't break considering how early it is into development at this stage. Thank you.
Thank you very much, Daniel.